Okay, guys, for the sake of speed, I'm going to keep horsing on. I just checked that answer for the degrees and I was right. It was about 10-ish degrees in the down direction, whatever. The answer we got was good. I also realised that I skipped one part of the question about the Fluctofia. The very last thing asks you to suggest an improvement to how they could improve the design of the Fluctofia. The easiest way there is to say just have the fire closer to the stones or cover it with a lid or something. I remember these were 5,000 years ago. They can't just make an actual bathtub, but best ways is to improve it or move the source of the fire closer or put a lid over it. Now, final question. I know this has pretty much been like a 40-minute class. It is what it is. Alright, so this is why I want to do this as a video rather than class time. So our final question was experiment 1. An experiment measured specifically latent diffusion of ice. Warm water was placed in the copper calorimeter. Dried melting ice was added to the warm water and the following data was recorded. So you have the mass of the calorimeter in water, temperature of the water, mass of the ice, blah blah blah. Okay, let's just do question by question. Explain why warm water was used. Basically, it'll speed up the melting of the ice, and it will mean that any energy lost will be negated by the warm water, providing with a little bit of extra energy. So energy lost to the environment would be negated by energy gained from the warm water, but mainly it's to speed things up, so it's to have the ice melt quickly. Why was dried melting ice used? Now, they're being sneaky here, because they're hiding two questions in one. It's very easy to skip part of it. So why do we use dried ice? Well, we use dried ice because we're measuring how much energy is required to cause ice to melt, right? Any drop of water that's on that ice is going to take some of that energy and throw off our calculations. So we use dried ice so that there's no liquid water being factored in. Excuse me. And we use melting ice to make sure that the ice is at 0 degrees Celsius. So it's not below 0. So it's exactly at 0 Celsius, which takes away, we don't have to worry about the temperature needed to raise the ice up to 0 from minus 10 or whatever it happened to be at. Okay, describe how the mass of the ice was found. Alright, well, the mass of ice could be found by taking the calorimeter of water at the end, when you've got the water and the melted ice, and then subtracting that from taking that value and subtracting the value of the mass of the calorimeter and the water, which will give you how much ice was used. So they measure the mass of the calorimeter, water, and melted ice, and subtract the calorimeter and water's mass from it. What should the approximate room temperature be to minimize experimental error? Well, you're looking at around 20 degrees Celsius. That's usually room temperature, or 25. Let's see, it's between the initial temperature was 30 and the final was 10, so about halfway between 30 and 10, which is about 20 degrees Celsius, roughly 20 degrees Celsius. That's room temperature. Okay, now I've gone on at length about the difference between the two ways to do these heat calculations, to either say heat lost by one thing versus heat gained by the other, and I know that I prefer adding the whole sum of the energies. This time they're kind of making you go down one route. And when I say making, they're kind of guiding you. So they're saying, what is the energy lost by the calorimeter and the warm water? And we're going to use that to find the latent heat of fusion of ice. So let's deal with, we'll follow their instructions. We have to. So the energy lost by the calorimeter and the warm water. Well, I cheated a little bit here. I've just written these out from an earlier version of this video to save us a bit of time. All I've done here is I've converted the mass of calorimeter, I've converted into kilos from grams, the mass of water. I've calculated that by taking the mass of the calorimeter in water was 118.8 grams. Subtract the 60.5, which is the calorimeter, and that gives us the 58.3 grams, which is the amount of water. And I've converted that into kilos. Initial temperature of the warm water is 30.5. The mass of the ice was 15.1 grams, or 0.151 kgs. The final temperature of the water was 10.2, and the initial temperature of the ice was 0, because we know it's just melting. So that's all the information we have. Flash player, go away. Remind me later, go away. Sorry, folks. So that's all the information from the question. The other things we know are that the heat capacity of copper is 390 joules per kilogram per Kelvin, and the heat capacity of water, this time they're giving us as 4200 joules per kilogram per Kelvin rather than 410. Okay, so first part of the question, what is the energy lost by the calorimeter and the warm water? Well, the energy lost by the calorimeter is the mass of the calorimeter times the heat capacity of the calorimeter times the change of temperature of the calorimeter. That's going to be the mass of the calorimeter is 0.065, the heat capacity of copper times the temperature change, and it went from, so the temperature change, it went from 30.5 to 10.2, so it's a temperature change of 20.3. This is where the difference between the two methods comes in. We don't have to worry about it being minus or plus in this structured way they're giving us. It's not always good, but we'll follow their instruction here. So the temperature change is 20.3, added to the mass of the water times the heat capacity of the water times the change in temperature of the water, which is also 20.3. And that works out as 5503.3375 joules, so 5,500 odd joules. So that's the energy lost by the calorimeter of the water. Now, we need to use that to figure out the specific latent heat of fusion of ice. So let's think what happened here. The heat lost by the calorimeter and the water will be used to melt the ice and then bring that melted ice water up to its final temperature. Sorry, running out of room here. Okay, so let's see what the heat needed to melt the ice. Well, that's the mass of ice times the latent heat of fusion of ice, which is the thing we're looking for, plus the heat used to bring the ice to its final temperature, which is the mass of the ice times the heat capacity of water, because that ice has melted now to be water, times its change in temperature. Okay, so let's put in some numbers that we know. The mass of the ice is 0.0151 kgs multiplied by the L that we don't know, plus the mass of the ice, which is again 0.0151 kgs, times the heat capacity of water, which in this experiment they've taken as 4,200. I'll leave out units for now. Times the temperature change. Well, it went from 0 up to 10.2. Now, when you add these energies together, we know that it's going to equal to the energy lost by the other stuff, by the water and the calorimeter. So that's going to be equal to 5503.32. Okay, so let's work out this and bring it to one side. So 0.0151 kgs multiplied by the latent heat is equal to the 5503 minus 0.0151 times 4,200 times 10.2. And look, while we're at it, we may as well get all the maths done in one go. Let's bring this fella across and divide it in. So the latent heat of fusion of ice is equal to 5503 minus this mess, 0.0151 times 4,200 times 10.2. All of this divided by 0.0151 kgs. All right, let's see, we're on the final stretch, folks. 5503 minus brackets 0.015 times 4,200 times 10.2 in bracket. That's divided by 0.0151. So that gives us an answer of 321,880. Now, we're done, but we need our units. This is the latent heat of fusion of ice, so that's joules per kilogram. How many joules of energy is needed to melt 1 kilogram of ice? It's 321,880. Is that the end of the question? It is. Good grief, what a long one. Right, guys, come here. Take her easy. Talk to you soon.